I'm Devin Malverde, and today I'll be discussing graphing polynomial functions. So I'll have a couple different definitions today, and for our first one, we'll be talking about a vertical shift, and also for the second one. The first definition is the graph of f of x plus c is f of x shifted vertically upwards c units. And the second definition for vertical translations is graph of f of x minus c is f of x shifted vertically downward c units. And for the next two definitions, we'll be discussing horizontal translations. And for this one, the definition reads graph of f of x plus c, and you notice the plus c is inside the parentheses with the x, which makes it a horizontal translation, is f of x shifted horizontally to the left by c units. Now this is a little bit odd because your c is positive, but when it's inside the parentheses, the translation will be to the left, which is on the negative side of the x-axis. And for the second definition involving horizontal translations, it is the graph of f of x minus c is f of x shifted horizontally to the right by c units. So for horizontal translations, when the c is negative, then we'll move it to the right, which is the positive on the x-axis. So now I'll demonstrate graphing the first two definitions we had. The first one being a vertical translation going up, and then the second definition being a vertical translation going down. And for the function, we have our parent function here at the top, f of x equals x squared. And for our function to graph, it's f of x equals x squared plus 3, which, as shown in the previous definition, is a vertical translation going up. Also, when going through the definitions, I'm going to move kind of fast because it's a review, so if you need to pause the video to write them down, feel free. Okay, and for the first definition here, we can see that the graph is translated upwards of 3 units because c is outside of the parentheses with x, which means it's a vertical translation. And since it's positive, you're moving up 3 units. And then for the second one, I'll graph now. And here is the second one graphed. You just bring down the parent function 3 units. It's similar to this one. The only difference is that c is negative 3, and since it's negative, you'll go down 3 units along the y-axis. Okay, and now continuing on to horizontal translations. Our parent function is the same once again, f of x equals x squared. And we'll start with our first function over here, and we have f of x equals x plus 1 squared. So as we discussed before, if c is inside the parentheses with x, then it'll become a horizontal translation, and since c is also positive, that means that we'll be moving over to the left 1 unit towards the negative side when we graph. So the parabola will shift 1 unit to the left. And that would be our first function being graphed. And we'll move on to our second one. And for our second one, we have f of x equals x minus 2 squared. And since, once again, the c term is inside of the parentheses with the x, but this time it's negative, it'll also be a horizontal translation, but it will be to the right. So we'll move the graph over positive 2 units. And remember, in these basic translations, that the only thing happening with the graph is its location. It's just moving. Nothing is happening to the graph where it's being stretched or compressed yet. And then we'll move on to our next definitions now. Alright, and now we'll continue on with our definitions. We'll discuss compression, stretches, and then we'll also discuss reflections among the x-axis and reflections among the y-axis. The first definition involving compressions is C. If C is greater than 1, then the graph of f of x is compressed in an x direction by the factor of C. So the bigger C is, the smaller your graph gets. And then for stretches, if C is greater than 0 and less than 1, so if C is a fraction, then the graph of f of x is stretched in the direction of x by the factor of C. And to continue on to reflections, the graph of negative f of x is the graph of f of x reflected about the x-axis. And then the graph of f negative x is the graph of f of x reflected about the y-axis. On these two, it's important to notice that the negative sign is outside of f of x on the x-axis, and then for the y-axis, the negative sign is inside the parentheses with the x. And now we'll continue on to graphing the functions. Alright, and now we'll be starting with our reflections. This is our reflection along the x-axis. We know this because the negative term is not inside parentheses along with the x term. And here we'll be doing a reflection along the y-axis. And we know, so along the y-axis, because the negative term is inside parentheses. So I'll start by graphing this for you, and when you reflect over the x-axis, you're reflecting downwards. And this is the resulting graph you would get. And now continuing on to our reflection over the y-axis. Now, you always have to keep in mind, if the negative term is inside parentheses, then that's how you'll know it will be along the y-axis. And also, when you reflect along the y-axis, you move your graph this way. And keep in mind, if you were to reflect a parabola, which is this graph right here, over the y-axis, then it would be symmetrical, like the graph will look exactly the same. But when you're doing polynomials to an odd power, or say like cubed or to the fifth, and you reflect that graph over, then it'll change. Alright, and now we're going to continue on to our stretch and our compressions. So first we'll start with our compression, and this one is a compression by the factor of 3. And I'll go ahead and graph that for you guys. Okay, and then we'll move on to our stretch by a factor of 1/2. And over here you can see we have a different parent function, which is x cubed instead of our previous ones we've used, which is x squared. The graphs are still on the same, like all the same rules still apply with all of the other definitions we've done thus far. And now I'll go ahead and graph 1/2 x cubed for you guys. And you can see on this one that we'll have a vertical stretch instead of compression, even though it is a fraction. And even though it stretches, the point should still intersect where it originally was. I made a little mistake there now. But if it was originally like on the origin of the graph, then even though it stretches, it should still intersect there. So now we're at our last two definitions, and we're going to talk about a vertical stretch and vertical compression. So if c is greater than 1, the graph of f of x is stretched in the y direction. If c is greater than 0 but less than 1, the graph of f of x is compressed in the direction of y. And of course, this seems similar to our horizontal in stretch and compression. The only difference is the graph will become, as opposed to this, shorter. Or longer. And I'll give you better examples in a second when we graph. Alright, so now for our last two definitions, we'll have our vertical stretch and our vertical compression. And you can see that it's a vertical compression because the terms are inside parentheses that are paired with the x, and the exponent is on the outside. So 2x, for example, you can see it's inside the parentheses while the exponent is on the outside. Now when you graph this one will be, like I said earlier, a vertical stretch. I'll go ahead and graph it now. Now when you're doing a vertical stretch, the length of the graph will increase, of course. And then when we do a vertical compression, which is next, the length of the graph will decrease. And I'll go ahead and graph a vertical compression for you guys. And you see the same graph, but it's just pushed further down. And with a stretch, it is pushed up. And those will be the last two definitions for graphing polynomials. And it's done with Vsauce. Thank you guys.